Good afternoon, sir. In this video I will be showing a Black and Becker attack on pkcs 1 version 1.5. so I have followed this paper to show this attack. So let's see the pkcs 1 version 1.5 format. So as you can see, in pkcs 1 version 1.5 the first two bytes are 0002. Then we have a random padding of 8 minimum size of 8 bytes, non-zero padding of minimum 8 bytes. Then we have a 00, this is called separator, and then we have our actual message. So for a 1024 bit key in RSA, we have a actual size of the message is 128 bytes. So in this padding, what will happen is this: this minimum random padding is 8 bytes, this is 2 bytes, this is 1 byte, so total 11 bytes. So maximum size of our message can be 117 bytes. So in any case, if our message size decreases, like suppose 10 bytes, then this random padding is increased. We must note that this is non-zero random padding. So in case of 10 bytes of message, this is 2 bytes, and then this message will be of 115 bytes, and then this is 1 byte. So this total size will be 118 bytes, 118 bytes, and this is 10 bytes of our message. So to attack this, so this Black and Becker attack, we will not use the actual cipher text, but we will use a padded plain text, and what we will do is we will multiply. This is our padded m is our padded plain text. We will multiply it with a random integer s, and we will call an oracle that will tell us that if the padding of our m dash is correct or not. So let's see the code. So this is the code I have written. This is the oracle. It will accept a text and it will tell us that if the padding of our m dash is correct or not. And this is our padded plain text m0. This is our modulus, and in our series size of this modulus is 1024 bit. And so let's see how this attack works. So as you can see that in this attack we multiply our padded plain text m with a random integer and send it to oracle, and oracle return us that is the padding is correct or not. So in this way we find our s1. Here. So as you can see, now m1 is our correctly padded plain text. Oracle has said that, and this is our s1. We have found our s1. Then from this we can deduce that m1 is something like m0 s1 minus rn. Now from this formula we can deduce this formula that r equal to m0 s1 minus m1 divided by n, and we can say that our r, the interval of our r can be lying in this. So when we found our s1, we reduced our interval of our message, that is m1 is lying in the interval 2b 3b minus 1. Now we have deduced that the r which this r can it lies in this range 2b s1 minus 3b plus 1 divided by n to 3b minus 1 s1 minus 2b divided by n. So now there may be many values of r lying in this interval. So for each value of r there will be an interval in which m1 will lie, m1 will lie. So what we will do is here we have found s1, and now as in this example you can see in this paper that the range of r is 12 to 17, that is 6 possible values. So for each possible value of r there will be different intervals. For each value of r there will be an interval. So in this code, as you can see, these lines are here we will finding the value s1. Then here these lines of codes for each possible value of r they are finding the interval, and we storing it into a set new m. So after finding the values And also note that we are initializing s1 from n divided by 3b. So as you can see that b is, we have started b as 2 to the power k minus 16. Since we know that the first 16 bits in our plain text are used for padding, so we can reduce our interval from 2 to the power 1024 to 2 to the power k minus 16. So after finding the interval for every r, what we will do is, now we will narrow down each interval, and if at any point we found that any particular interval, like say a b, in any particular interval a b, if a equals to b, then we have found our message and we will print out a. So this our m0 initially lies in this interval, and for each r we will narrow down this interval for m0. Also we will update our r in this way. So at the end, when we will have only one interval, all intervals are discarded and we will left down with only one interval, then we will do a binary search on that interval. And then when we find an interval such that a equals b, then we will output a. So in this code you can see that here I am narrowing down each interval such that if I find any a equals b, then I will it will print a message that message has been found. Then it will call compute message with this interval hex string str new b, and it will print our message. This is compute message function. It will simply remove the padding from the message and it will print the real message. And here you can see that for each r I am for each r and for each r we are trying with the different for each r we are trying with the different values of mi, and thus we are sending the many padded plain text to Oracle, so that Oracle returns true or false. So in this way we are narrowing down our s value, so that we can narrow down our interval here. So after each iteration our s1 is being updated. So let's run this code and see how it works. So as you can see that it has narrowed down the interval, and our correct message is printed, that is NIT Calicut. So as you can see that our final updated value of s is this, and at each interval, like this is just our n minus that's the previous interval. So you can see that 76L and here it is 77L, all the previous values are same. So in the next iteration, that is in here, it has probably become equal. It is, if I have printed the intervals here, then we can see that the intervals are equal. So this is it for this Black and Becker attack. Thank you.